Oi, loss of plasticity in deep continual learning. Pretty cool paper here today. So they get into continual learning and the issues of forgetting and loss of plasticity and like the model's difficulty to learn new things. They create a new data set that's good for that and pretty simple. They go over different existing techniques that already kind of solve this problem partially and why they do so, as well as make their own technique that actually kind of gets us across the finish line in this sense. It is not perfectly computationally efficient or anything, it's like in that sense. But if your goal is making sure your model can just keep training and keep picking up new tasks and more new tasks and never stop training, then this is super useful. Disclaimer. Before we start, remember to like, subscribe, comment, share, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, support me either through Patreon or YouTube. For as low as $1 per month, you can get early access to my videos, or for a one-time payment, hit my Venmo. And if you'd like to borrow my brain for an hour or two, book a consultation call. All links are over on my Linktree. Let's get started. So, deep learning models have, in general, a lot of trouble adapting to changing data. This is most architectures, right? And because of this, in almost all applications, they're usually restricted to a special training phase that comes first, where you make the model actually good, and then you stop said training phase. You turn it off when you want to actually use the model, and usually you can't even really keep training it in the same manner that you were anyways. It introduces all kinds of problems with instability and forgetting things and just having trouble learning more things if you try and do that. So when you do get new data, you usually have to just make a new model and start training it from scratch on all of your collective data, old and new. It's been a pretty persisting problem that is not super well understood, no clear solutions. There's a bunch of little micro solutions in certain areas to do certain things, but no real overarching way to get us models that can just continually bring in new data with no issues. In this paper, they're going to analyze how exactly it is that standard deep learning methods lose their ability to learn with extended training on new data, and they're going to call this a loss of plasticity, referencing brain plasticity in actual biology, right? And in biology, plasticity is the idea that if you have a lot of mental plasticity, you are very adaptable. Your brain can pick up new lessons, new ideas, new goals pretty easily. Whereas less mental plasticity, which, for example, happens in neuro disorders and whatnot, but more notably, more commonly experienced is just aging. When people get very, very old, they tend to also lose a lot of their neuroplasticity. And the idea of just picking up new things gets much harder for them. For those of you who are already aware of this continual learning subfield, this loss of plasticity phenomenon is different from catastrophic forgetting. Catastrophic forgetting is when you do try and keep training a model and you find that all of the old stuff it used to know, it forgets. It has lost due to your training on the newer data. And that is also an issue, of course, but not the one they're addressing here today. Here they care about how good is the model at picking up new things and less about how do those new things mess with the old things the model knows. And the authors managed to find a simple change that enables them to maintain plasticity indefinitely in both supervised and reinforcement learning. And it's exactly like classical backpropagation for the most part, except that a tiny proportion of less used units are reinitialized on each step, much as they were all initialized at the start of training. By that we mean a given either individual parameter or entire vector, entire row of parameters in a given weight matrix is reinitialized, as in like set to random values back like how it was at the initial startup, right? And this just happens occasionally and happens to a very tiny proportion of the parameters over each training step. Very, very tiny proportion. And you're effectively just, this is a different source of randomness than the other ones we already have in training. And this source of randomness is actually perturbing the parameters themselves as opposed to stuff like dropout, which is perturbs the actual residual stream of said models. Now, to test this, they need an actual data set that works with this whole continual learning regime, aka like is actually set up such that you are continually adding new things to be learned, right? So they adapted ImageNet and turned it into a sequence of binary classification tasks by taking classes in pairs. So ImageNet is, I believe, 1,000 classes, right? They just grabbed a bunch of random pairs of those 1,000 classes and said the model is not going to have to regular full multi-class classify all 1,000 in a given time at once. They actually just show them in pairs and they say which one of the two is it for a bit, and the model experiences just the pair for a little bit before moving on to the next pair. So, example, distinguishing cats from houses is might be the first task the model gets, and the second could be distinguishing stop signs from school buses. And given how combinatorics works, you start out with 1,000 initial classes, you end up with 500,000 binary classification tasks, right? Every combination of those thousands. They call this continual image nets. I could be wrong. I do think they open source the actual data set setup. If not, it's simple enough to replicate on your own if you'd like to. And a key thing to emphasize here is that since we're just iteratively adding or switching to the next task, the next binary classification, the actual difficulty of the tasks remains the same over time. I mean, there's some variation, I guess. Maybe if it's easier to classify bicycles than it is dogs, then there is a little bit of variation, and like certain classes could be a little bit harder than the other. For the most part, though, not really. And on average, definitely, you should expect the actual difficulty of these tasks the model is switching to every few iterations stays the same. And with traditional techniques, traditional backpropagation, right, you would actually expect, given what we know, that on the first class it would do pretty well, second class almost, and then the performance would degrade to where even though the tasks have the same difficulty over time, traditional techniques would result in the model just doesn't have the ability to learn new things, basically. And that's what we're talking about when we talk about loss of plasticity. And with those traditional techniques, they tried a bunch of different models and hyperparameter searches and everything, and they got up to 88% correct classification on the test set of the early tasks, meaning the beginning of the process of just the first few ones being learned. They hit as high as 88% accuracy, but then as they kept going and going and going and switching to new tasks and new tasks, new pairs of images to classify, by the 2000th task, they had lost substantial plasticity for all values, for all models, such that for even with a well tuned model, they saw performance first improve, especially as you get like just a couple tasks going and it can kind of get more general representations to use across tasks. So it's at first in its improvements and then begins to fall substantially, ending near or below the baseline, which is just a simple linear model. You can see that right here. A linear baseline's performance is a bit above 75%, 77 or so. And across different actual step sizes, these models started off improving and started off better than the baseline, but slowly lost their actual ability. And smaller step size did seem to help. I guess it's not messing with the actual parameters enough to ruin things per se, but even then, it is definitely below an initial much better value in the test set. Now, there was an exception, is that when you take algorithms that actually keep the network weight small, then we do actually maintain plasticity. So weight decay, really. And we know weight decay is super useful and everything. Not super surprising there. And it is good to see we do have this and it does work. It's being used. So in a way, it is its own, weight decay is its own partial solution to this loss of plasticity problem that we've already been implementing. And given that weight decay is so common, it would be fair of you to say, shouldn't the baseline include weight decay? And yeah, I kind of agree. To that extent, they are giving themselves an easier baseline than they otherwise probably should be using. But even though weight decay already pretty much solves this, we can hopefully improve over weight decay, and we can hopefully learn about what's actually happening and what's important and why weight decay works, would be the hope with this, right? Speaking of other methods we already use, though, atom, dropout, and normalization actually increase loss of plasticity when you add in those parts of a network, those methodologies. What you get is a model that is bad at picking up new tasks. But so with weight decay, what's actually happening here, right? Well, it seems like small weights allow the network to remain plastic, high plasticity. And then another method that also helps is what they call shrink and perturb, which I believe is from some prior study. And it is just L2 regularization, so weight decay, plus small random changes in weights at each step. They are adding in randomness to the weights, more stochasticity outside of what gradient descent and weight decay are doing that is purposeful. They're adding in some randomness. And this injection of variability into the network of the randomness reduces dormancy, meaning neurons and whatever that go dead, ranks of matrices that collapse, and increases the diversity of the representation. When you add in that randomness, you're more likely to actually pick up and create a new circuit that could be useful. So they make a new variant of the backpropagation algorithm that is explicitly designed to do this, to inject variability into the network and keep some of its weights small. As a refresher, conventional backprop has two main parts that are relevant to what we're talking about here. First up is initialization with small random weights. So before training starts, all of your weights are small and random. But then after that, you don't actually use any kind of randomness or any way to force them to be small unless you're using weight decay. And then, of course, gradient descent following the gradient, right? Trying to optimize our actual loss function. So that initialization point that is random does provide variability initially, but with continued training, that variability is lost and the plasticity along with it, right? Meaning the model's actual parameters collapse into fewer effective dimensions, lower rank. They get stuck in a rut with what they are doing, the circuits they've already made, and lose the ability to create a brand new circuit for the brand new task they may come into contact with. So to re-inject variability, this new algorithm they're proposing reinitializes a small number of units during training, typically fewer than one per step. They're saying units, I'm not sure if they're referring to individual parameters yet, or if they're referring to actual full-on neurons, like a full-on row of a parameter matrix, of a weight matrix. But the point is, a very, very, very small portion of the model on any given step could get this random update, random reinitialization. And to prevent disruption of what the network has already learned, only the least used units are considered for initialization. So they actually try and find what part of the model is being used the least, has the smallest effect on the actual output. Let's only reinitialize that part. It is the least likely to be useful and therefore the least likely to mess with the model as it currently stands and make it catastrophic forget and all that stuff. In testing this new technique, they did find that it mitigated loss of plasticity in continual ImageNet while outperforming existing methods. Not to say that you should use it instead of weight decay or something, but like, use both, right? The question being, how do they actually define this metric of rarely used and how often do they do the updates? What's the actual implementation details, right? So their utility measure, they call it contribution utility, is defined for each connection or weight and each unit. Already off the bat, you're defining it for every single weight. This sounds computationally expensive. Is this worth it? I mean, I haven't actually done the code to go see. Already kind of doubting it though, right? That sounds pretty expensive. But the basic intuition behind it is that the magnitude of the product of the unit's activation and outgoing weight gives information about how valuable this connection is to its consumers. So this is like a heuristic right here. We assume that magnitude corresponds with actual utility. Although key thing here, this is also a local measure. It does not require we do all the way up to the loss function or anything. It is only checking the utility of a given weight in reference to the consumers of that weight, just the next step in the actual model, right? Some more behind this magnitude heuristic, the idea being that if the contribution of a hidden unit to its consumer is small, its contribution can be overwhelmed by contributions from other hidden units. So I said heuristic, but like magnitude sounds reasonable to me. It's literally contributing less to the actual next step of the model. So they define the contribution utility of a hidden unit as the sum of all the utilities of its outgoing connections. More specifically, it's a running average. Now, what this says to me is it does sound like they are holding in memory effectively an entire extra model's worth of measures. So you already have the model itself to hold in memory. You already have its gradients to hold memory. That's times two. Then you already have also, if you're using Atom or Atom W or something, the momentum, right, to hold in memory. So you're already times three. I think this is an additional, so bring us to a total times four memory size if you include this. So odds that it's actually worth using. I mean, in the current pre-training regime, if you're fine with pre-training, probably not. If you really need continual learning, though, this may be worth it. So, anyways, now that we have that measure, they check that measure of usefulness for the entire model, and every iteration of training, they reinitialize a very small number. I believe it's one or even like less than one on average of the actual parameters of the units. Sorry, of the, I believe that's vector in a weight matrix. And when we reinitialize it, what we're doing is setting its outgoing weights to 0. Now, this is kind of weird here. So you're not actually adding in new random weights per se. You're really setting them to 0. This does, it's supposed to ensure that the weights newly added hitting units do not affect the already learned function, which, okay, cool. Like I would get this if you were growing the model along some dimension or something. When you do so with zeros, that does in fact maintain the output function the exact same. But here they're taking numbers that did exist, actual parameter floating point values that were non-zero, and setting them to 0. So really, wouldn't that already affect the learned function? I get that we're affecting it only a little bit because we chose the smallest magnitude one, so it should be affecting it only a small amount. But why don't we initialize randomly with a sufficiently small standard deviation of the newly initialized parameters? That's what I want to know. I'm tempted to think that that would be useful as opposed to straight zeros. But anyways, they went with zeros, and I'm not sure if they actually tested what I'm talking about or not. I don't remember them mentioning it at all, so we'll see if they do. But a new problem is added. When you initialize the outgoing weight to 0, that makes this new unit vulnerable to immediate reinitialization on the next training iteration because it, like, will by definition have 0 utility, 0 actual magnitude to its next output, right? A vector of all zeros is not going to contribute a whole lot of literally anything to the next neuron in the output. So they have to add in another thing, which is a way to protect the new units from immediate reinitialization. So they set a maturity threshold M. So for M number of updates, that unit is actually not in contention to be reinitialized. I don't know how they're storing this in memory. I would assume they have some kind of indexing structure, so they're not actually storing it in a full-on like another model size of a bunch of like of a mask. That would be terrible. I'm assuming some kind of indexing structure, I would guess, of the actual of the vectors in weight matrices, so that it's not a full model size. It is some RAM though. That is some RAM to keep track of, right? And every time that they do their training iteration with a check of the lowest magnitude contributions, now suddenly you've also got to not just grab the lowest one, but grab the lowest, check if it's not in its maturity threshold. If it is still in its little safe zone, safe time period, go to the next smallest one, right? So again, computationally, uh, not too fond. I really hope that you really need continual learning here. And now, on every single step, a fraction of mature units that are older than their maturity threshold have spent a long enough time not having been updated, right? Row, I believe it's P. I think it's a row. It's been so long since I took actual math classes. Oh my god, I used to know that alphabet by heart. Let's call it row. Anyways, a fraction of the units called the replacement rate is reinitialized in every layer. And this replacement rate is typically set to such a crazy small value that in reality, after hundreds of updates, I assume by update they mean training iteration, like hundreds of batches, right? Only one unit is replaced. So they're replacing these things very, very rarely in reality. This P is below the actual number of parameters in the model by quite a good margin. And I've been complaining about computation here. They do point out that if you're using mini batches, you could choose to instead average over the mini batches instead of keeping a running average as a computation. Assuming you're either doing mini batches to get a huge batch size, then that should be a good enough average. But if you're only doing a batch size that fits on RAM, then you kind of need to average over multiple batches. I think I probably would attempt to go this route instead. Sounds a bit better. Although I think, is that just flop saving or is that a compute saving? I don't think it's compute saving. I'm not gonna think about it though. I'm already getting pretty tired from this paper. And what I really would have liked to have seen from this paper, maybe I missed it in an appendix somewhere, is an actual detailed analysis of the memory and throughput's runtime increase. That would have been nice. I may have just missed it, not gonna lie. I didn't bother to read all the appendices or anything, but I would definitely have appreciated that to be highlighted front and center, because this is a huge problem with techniques in general. Is sure, your thing might work by a 2% or something, but if it also sacrifices actual compute by like 30%, then what's the point? So now we're going to talk about, why does backpropagation lose plasticity in continual learning problems, right? What's the actual cause of this? Because the learner loses this ability of plasticity over time, right? And the only difference in the learner, the model, is the its weights, right? I guess also the optimizer state if we're doing not just SGD. But we're going to focus on the idea of the weights here. Now, in the beginning, the weights are small random numbers sampled randomly from an initial distribution, but eventually they get optimized to the most recent task, obviously. And it's this difference. The starting weights that are random are qualitatively different from the actual weights of the model that has learned the task, or in this case of our data set, of has learned the first task in our series of many tasks to learn, right? And so what in what way have the weights changed such that they are suddenly bad at learning new things? And what are the properties of that initial random distribution that allow it to learn new things as opposed to our already partially trained distribution? Could be stuff like the diversity of units, non-saturated units, small weight magnitude, etc. And so when we actually look across the graphs over the course of training of what seems to match up with this loss of plasticity, the first noticeable thing that occurs concurrently is the continual increase in the fraction of constant units. Constant unit being one where the gradients flowing back from that unit becomes zero or very close to zero, meaning they're no longer really being trained. The gradients are such that they have hit a kind of probably a saddle point or something, either a saddle point or an actual local global minima, such that they now have zero gradient, right? Now, this unit, by definition, if it has zero gradient, that sounds like zero plasticity to me. Like literally not learning anymore, right? Now, how do we actually get zero gradients? I mean, technically, you could be, like I said, local minima, global minima, saddle point, whatever. In reality, or in at least if you have actual ReLU activations or ReLU like activations, the even worst case of this happening is when you have those activations and the output of the activations is zero for all examples of the task. So don't get me wrong, like the minima or saddle point could be the case, but dead neurons obviously are a much worse case of this happening, of when the model, like at some part of it, stops learning, right? And that's just for ReLU, is when it's all zeros. But for like other activation functions too, generally most of them do have some kind of vanishing gradient phenomenon at some part of the actual domain. Like in the case of sigmoidal activation functions, this is when the unit is too close to either of the extreme values. So too high of a positive number input or too high of a negative number inputs. It just ends up being a 1 or a 0 with practically no slope. So in the case of ReLU, you would say dead neurons. In the case of sigmoidal activation, you would say saturated neurons. And could, I don't think they mentioned this, but I mentioned it, could just also be saddle point, local minima, global minima. So, meaning that methods that stop the units from dying can substantially reduce loss of plasticity. Duh. And that's all well and good. I believe methods like that to some degree already exist. Well, obviously, yes, they do. Like leaky ReLU, for example, like fantastic. Or even just nowadays we use silo, glue, whatever, that are less likely to actually stay at zero. And then another phenomenon that occurs with loss of plasticity, another actual metric that goes concurrently in the graphs with loss of plasticity, is the steady growth of the network's average weight magnitude. So you would assume at random initialization that, especially with low standard deviation, that all of the weight magnitudes of a given vector in a weight matrix would be pretty small, right? And that they'd be roughly random in direction as opposed to magnitude. But over training, we do see, on average, a growth in the average weight magnitude. And this is a problem because it's already known that large weight magnitudes are often associated with slower learning. I believe it's because of what I said earlier with the whole saddle points and minima type issue. I'm not quite sure though. And think about this whole weight magnitude thing. This is, I mean, this is coincides with, of course, weight decay, right? Like that's what lowers the weight magnitudes, like directly encourage them to get smaller, right? So, and we did say earlier, weight decay does help with the increasing plasticity. So this all makes sense. Then the last phenomenon that kind of moves in lockstep concurrently with loss of plasticity is the drop in the effective rank of the representation. So, refresher, rank of a matrix is the number of linearly independent dimensions, right? The actual components that make up that matrix in terms of can span it. So the effective rank of the representation basically takes into consideration how each dimension influences the transformation induced by a matrix. So a high effective rank indicates that most of the dimensions in the matrix contribute similarly to the transformation induced by that matrix, right? High effective rank means the entire matrix is actually being used roughly evenly, but low effective rank meaning a small portion of the actual weight matrix is really doing all the heavy lifting, and that matrix has a lot more capacity in terms of subspaces being spanned to actually work on the residual state that is not being utilized. They found that in their experiments, the loss of plasticity was accompanied by a decrease in the average effective rank of the network. And now, low rank isn't necessarily a problem in and of itself. After all, low rank solutions are efficient solutions that we could maybe even pull out of the model and create a smaller model with, or something. Like if they're literally using a smaller subspace than what they could possibly use their actual full matrix rank, then it's not the worst thing in the world. It means the model is finding a simple, elegant solution, right? However, this low rank might be a bad starting point for learning from new observations because most of the hidden units provide little to no information, right? So when you have low rank, all those unused ranks are now effectively not useful as starting points to help in a new task you're trying to learn. You've already learned the previous task, and that's your low rank solution. Those a couple small number of ranks are all being used, right, for that solution. But then the rest of your ranks are just like the rest of your potential subspaces that could be spanned inside this weight matrix are just not useful, not being used, and not set up in a way that they actually are primed for initialization, right? But they're not initialized in a way that is primed for new learning. So we could explain this loss of plasticity in the following way. After each task, the learning algorithm finds a low rank solution for the current task, which then serves as the initialization point for the next task. As the process continues, the effective rank of the representation layer keeps decreasing after each task, limiting the number of solutions that the network can represent immediately at the start of each new task, right? So, like, gradient descent does favor these low rank solutions, and these solutions themselves are efficient and pretty and everything, but they just are not good starting points for the next task that we try and add on. And just to be clear, we've said a couple things so far. Each of these correlates, each of these metrics that move in lockstep with the loss of plasticity partially explains that loss of plasticity, right? And the one that they have effectively messed with experiments today was the low rankness, whereas weight decay was already fixing the magnitude of the vectors issue. And dead neurons, I believe, I could be wrong, are less of an issue nowadays that we're using SWIGLU, GGLU, whatever in our MLPs. Before we wrap up, a few little bits of the actual discussion section of the paper. To be clear, and this does not tackle the forgetting problem. This idea of randomly reinitializing weights does not help with that. Although they do propose the idea of what if we made a long-term measure of utility that could remember which units were useful in the past, and that's all they said. Maybe are they referring to like reinitializing those old parameters? Are we storing them or somehow? Like what's happening there? I'm not quite sure. But it's interesting to say like if utility actually does measure the thing you're measuring, then pulling up that past utility, I guess, could be useful. But it's like, okay, do you replace the currently existing vector in that weight matrix? Then what are you suggesting here exactly? I'm not quite sure. But they're just hypothesizing here. They also in this paper did not take into account speed of learning. That was not looked at all. And so it's not clear how these methods affect that. And then the type of loss of plasticity studied in this article is largely because of the loss of ability to optimize new objectives. This is different from the type of loss of plasticity in which the system can keep optimizing new objectives but lose the ability to generalize. That's an altogether different issue. And it is unclear if these two types of plasticity loss are fundamentally different or if the same mechanism can explain both phenomena. They just didn't delve into that in this paper here today. It could be the case that their method solves the generalizability issue, but they have no reason to think so. They didn't test for that. And then limitations. Their utility measure is based on heuristics, the idea of the weight magnitude mattering so much, whereas they weren't actually affecting the rank. They're doing weight magnitude, but they were effectively thinking it probably affects the rank in this way. And it is not a global measure of utility, it's a local one, which computationally I think is cheaper, but might not be actually optimal performance wise. And then, of course, performance efficiency trade off is a whole separate issue. But they do suggest it might make sense to develop utility measures that propagate backwards from the loss function, similar to how we already backpropagate gradients across the graph. Now, here's what I wanted to get to the whole time, uh, is this hypothesis that the loss of plasticity might be connected to the lottery ticket hypothesis. The hypothesis states that randomly initialized networks containing subnetworks, or do contain subnetworks that can achieve performance close to that of the original network with a similar number of updates. So a low rank version. The idea here is that the random initialization, right, at the beginning of the start of training, that already contains subnetworks that are pretty good. Like, because the model is so damn big, there's so many parameters, there's so many possible sub routes for the model. If you were to remove certain weights entirely and not have to do dense operations, that there are some sparse subset just by random chance inevitably could perform the task pretty well, and that it's actually that part of the network that we're actually updating, and that becomes the low rank, well performing actual solution, right? And that the rest of the parameters effectively get diminished to zero or reduced utility or cancel each other out or whatever it is, turn into noise, that kind of thing. And that the hypothesis states that it's those little winning tickets that are actually useful. And so for the initial task that you train on, right? You start training for your initial task and you grab the winning tickets related to the current initial task, and the model closes down its rank and effectively becomes just that winning ticket. And next thing you know, you set up your new task, and there are not a bunch of potential tickets in the model because all parameters that were not part of the original winning ticket have now just lost their contribution to the actual model. They are no longer part of the low rank solution. They are part of all the ranks that got ignored, basically, right? So the idea being that this method they developed with inserting randomness into the weights occasionally actually reintroduces new potential tickets that could be winning tickets, thereby allowing the model to keep learning. And that is my personal favorite explanation of what is actually happening here. Let me know your thoughts in the comments below, I guess. Like, subscribe, all this stuff. Do I usually say that at the end of the video? I don't think I usually say that. I'm pretty sure I usually just say end of video. Yeah, end of video. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below. For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.